The first thing we have to figure out for problem 13.5 is the shear forces to the right of points A, B, and C. So we are going to want to figure out with what forces this beam is being supported. So these supporting forces are going to be straight up at point A, and there's going to be a vertical and a horizontal component at point C. Let's call this force R for reaction at A, and reaction C in the y direction. So we have these two unknowns, and we're going to use the sum of all moments equals 0 to figure out what they are. So in order for this equation to only have one unknown, we want to look at a point where, let's say here, point C, where RCY is going to be 0. So if we look at the moments around point C, we know that RCY is going to contribute 0 moment because its moment arm is 0. It has a 0 distance from this point. So summing up all those moments from the right, we have a force of 2.4 acting at a distance of 4 feet from point C. And we're going to say that's negative because it's a clockwise torque. And as we go from right to left, the next force we get to is the one from the support at C, which is going to be 0 because the moment arm is 0. That force is right at C. And so that we don't have to put anything there. That's what I was talking about. That variable disappears. That variable doesn't even show up in this equation. The only one we're going to have is this RA. The next one we get to is a counterclockwise, so I'm going to put plus. The counterclockwise moment from this horizontal 3.6 force, and that is 2 feet above point C. Then we get all the way over to the left, we get a clockwise moment of force RA times the distance of 12 feet total from point C. And all that is equal to 0. So when we solve that expression, that whole equation for RA, we get negative 0.2. And the unit of force we've been using is kip. Negative value, what does that mean? Well, we had assumed that RA was pointing up, but it must be pointing in the other direction since we got a negative upward value. So actually, we really have to draw that force vector downwards. Now to find RCY, we can say that the sum of all vertical forces equals 0. Let's start from the left to looking at our force on the left here. We just figured out that was 0.2, right? And since it's downward, let's call it negative 0.2. Moving to the right, there is no horizontal, no vertical force at B, and we have to go all the way to C. RCY is going up, and then we have another downward force all the way on the right, this 2.4 going down. So from that we can find that the upward force at C is 2.6 kip, going up. So here's where we get to the new stuff. So here's an important point of this chapter, is that the shear at any point, we're looking just to the right of point A here. So to find the shear, you just look at all of the shear forces to the left of that point. So we're going to call the positive direction up, and this is the sum of all shear to the left. So there's a sign convention here from this arrow. That means that any shear forces to the left that are upwards are positive shear. Any shear forces to the left are downward shear. The way I think of this is that positive shear kind of comes from, like, if somebody's walking on this beam. If somebody were walking on it, there was like a big load in the middle, then that would cause the support on the left to push with a force upward on the beam, and that would be positive. But here the force at the supported A is actually downward, so we have a negative value, and that's the only one. So the shear here is negative 0.2 kip to the right of point A. So here's how we apply that equation to the just to the right of point B, which is right about here. We still look at all the shear forces to the left of right here, and we see that we still have the negative 0.2 kip from point A, and then at point B there's nothing that's vertical. This 3.6 kip force is horizontal. So that doesn't contribute to the shear, that would just contribute to an axial stress. So we're still left with just this negative 0.2 kip. Okay, for A and B, I said that the shear at the point to the right of B equals the sum of all the shears to the left of B. I didn't mean of B, I meant of that point. So we were looking at this point, so we were looking at all to the left of that point, which includes B. So here, we're looking to the right of C, so when we look to the left of that point, just to the right of C, that includes the shear at point C. So here we have another shear added. We have our negative 0.2 from all the way on the left of point A, and then we have a positive, because it's up, 2.6 acting at point C here, for a total of 2.4. Reasonability check. This 2.4 is equal in magnitude to the 2.4 force at point D, so that makes sense. If those weren't equal but opposite, that would mean that this beam wouldn't be in equilibrium and it would be accelerating up or down. The next part of this problem is to find the moment at all these points. So the approach to that is similar to the approach for finding shear. So only in this situation, the positive sign convention is clockwise. So we have to sum up all the clockwise moments to the left of A. And we see that there aren't any, because the beam ends right at A. So that's just zero. And this is something that's consistent among all problems. At the very ends of a beam, the bending moment is always going to be zero. The next thing we have to find is the bending moment just to the right of B. And the reason I say just to the right of B is that so we know we're supposed to include this 3.6 kip. So again, we're going to sum up all the moments to the left of the point, just infinitesimally to the right of point B. Infinitesimally to the right, meaning that if there's 8 feet from A to B, we can assume there's 8 feet from A to the point to the right of B. And we're going to use that 8 because that's the distance from this force at point A to that point, and this force at point A is causing a counterclockwise torque, so this is a negative value. And there's another negative moment from this 3.6 kip because it's trying to rotate around point B counterclockwise. So we're going to subtract the 3.6 times the distance from that force to point B, which is that 2 feet. And we add those two negative values together and it gives us our answer for the moment at point B. And another note about sign convention of the moment. The reason we're seeing clockwise as positive is because it corresponds to the sign convention for shear. So this is also the kind of moment you'll see if somebody is walking on a bridge, is walking on this beam. Again, if there was a big load, really big person walking on this beam, then the support would push up, which would be a clockwise moment around that point. Another way to think about that is that if you got a big load and it's causing positive moment, you're going to get a bending kind of like this, so that there's a tension at the bottom and a compression at the top. Another way to think about that is that if there is an external moment applied clockwise, which we're saying is positive, that internal moment that we're concerned about, that internal moment that we're finding inside the beam at point B, is in the opposite direction, the counterclockwise, which we have considered positive. Okay, so we're moving right along to find the internal bending moment just to the right of point C here. So we just passed another force that's going to apply a moment. Or, no, I was wrong, we didn't actually pass it. The question says exactly at point C. So that means that since this force, the 2.6 kip at point C is going through that point, there's zero moment arm, so zero moment from that 2.6 kip. So we're still just looking at the 3.6 and the 0.2 over here. But it's not going to be the same value as at B because the moment arm is increased. So the moment from the 0.2 is now we're going to have that negative 0.2 force times the distance from C, which is now 12 feet. And then we're also going to subtract the force of 3.6 times its distance, which is still 2 feet, because we're looking at the distance parallel to that force, or sorry, perpendicular to the force, which happens right here. So that's still 2 feet. So we add those up and that gives us the answer, negative 9.6 kip feet. Another way we could have thought about this is adding up the moments to the right of point C. But if we look to the right, then we'd have to use a sign convention where anything counterclockwise is positive. So if we look to the right of point C, we see that 2.4 kip force at point D, and that's negative because it's not a counterclockwise moment. So it's that 2.4 negative times the distance of that force from C, which is 4 feet. And that's also negative 9.6. So reasonability check, I think we did it right, because we got the same answer summing up from the left and summing up from the right. That leaves only one more thing. What is the moment at D? And this is pretty easy. We can just say that there's no moment at D because there's no force to the right. There's no forces to create any moments to the right side of D because there's nothing there. So there's just 0 moment. And that's, again, at the ends of a beam, there's always going to be 0 for your internal moment.